Okay, so here we're looking at a half-life problem. And what we usually need to do when we have an exponential model like this is we have a couple variables. Usually we have to plug in some numbers and figure out what k is first. Now, the way we do that is by going through the information they give us. Given an initial amount of A grams in this isotope at time t equals 0, find the exponential decay model. It tells us that we have a half-life of 48 years. So what that looks like, and again, we're going to say that A of t, actually let's simplify it a little bit. Let's say just the ending amount, I'll take out the function notation, is equal to the beginning amount, A sub 0, divided by e to the kt. Now, back to the problem that we just did, if we do the division of A sub 0, okay, what they're telling us is on the left-hand side, we're going to have 1/2. And the book shows an example. I typically don't do this when they tell us that we've got a half-life. You know, so our amount diminishes to 1/2 of the original amount. We just start out with 1/2 on the left-hand side. And that will happen over a course of 48 years. Notice how everything but k has numbers on it. And now we can just solve this equation. So the thing we're solving for is k. It's in the exponent. I'm going to apply a log of the same base as that exponent. So I'm going to apply a natural log to both sides. So I get ln of 1/2. And I'm just going to write that as 0.5. It's easier to put in on the calculator. Is equal to... Now, when I apply an ln to e, the e and the ln cancel. Again, I'm not going to be showing that work very much anymore. 48k. So all we have to do to finish solving for k is divide both sides by 48. So we get k equals ln of 0.5 divided by 48. Now, I strongly recommend you leave it exact. It says round k to 3 decimal places, but we're going to use that in a bit in the second part of this question. So we are going to throw that in the calculator. ln 0.5. I'm going to close that parentheses. Make sure you do that. And round it to 3 decimal places, we have negative 0.014. Now, we can use that number, but I think this will work out better if I use the exact. So just use the function above to calculate the time required for the isotope to decay to 1/4 the amount of A. So we're going to just start with a 1/4 here, equals e to the, now my k, I can write negative 0.014, and you'll see that. Let's go ahead and put that in, times t. But what I noticed is if I don't use the exact amount, then my rounding on the answer on the quiz on the computer won't be recognized as correct. So how do I solve this? I'm going to apply, well, I'm going to go back to using the exact value for k, sorry, e ln 0.5 divided by 48 times t. I'm going to apply an ln to both sides. That gives me ln of 0.25 is equal to ln of 0.5 divided by 48 times t. So I'm going to divide both sides by ln 0.5 divided by 48. And I will get t equals, switching sides here, ln of 0.25 divided by ln of 0.5 divided by 48. Now, I'll warn you, when you put this in the calculator, and again, you have to get the rounding right, to get the number right to enter as a decimal into the quiz, you have to put parentheses around the denominator. Otherwise, it won't do it in the right order of operations. So we've got ln 0.25, ln 0.5 divided by 48. Okay, close that parentheses, put a division in. Put in a parentheses, and ln 0.5, close the parentheses, and divide by 48. And now I have to close the parentheses on the division in the denominator to get the number 96. Well, no rounding at all. Had I used the decimal approximate, which is negative 0.014, look what happens. Well, maybe it'll work out. We'll see. All right, well, I sure didn't get the same answer, and that's because I'm rounding to 3 decimal places on my K, and I shouldn't. It's not going to accept 99. The quiz on the computer is not going to accept 99 as the correct answer. So leave it exact. Let's end this problem. We'll see you on the next video.